A person standing on a force plate in preparation for a jump has a free body diagram that includes their weight pointing down and a normal force pointing up. Newton's second law says that the sum of the forces is equal to the mass times the acceleration. And if we remember that acceleration is defined as the change in velocity with respect to time, we can rewrite it this way, where the sum of the forces is equal to m dv dt. Expanding this expression then in terms of our free body diagram, we have the normal force, which I'm actually going to rename the force in the z direction because we're talking about what the force plate is measuring. So we have the force in the z direction minus the weight of the person, mg. So Fw is the weight of the person, mass times acceleration due to little g gravity, times m dv dt. And right now we're talking about the sum of the forces in the y direction. In the z direction. We can rearrange this and integrate so that we get an expression for the velocity in the z direction that's equal to little g times the integral of fz divided by mg minus 1, all of this integrated with respect to time. We can then consider the different phases of the jump and consider that there are a couple of really interesting points to consider. In particular, there's this point at takeoff, there's this point where we're in flight or in the air, and then there's this point where we're at T landing, the takeoff point. And if we consider the force that the body experiences, that the force plate measures down here underneath the person, while they're in quiet standing, we'll just measure body weight. And then as they crouch down, the force starts to decrease, go below zero as they move downward. And then as they start to drive themselves upward, the force will go up above body weight, and then it will precipitously fall off as they hit the takeoff point. So right here, there's a takeoff point where the force precipitously goes to zero. So this line here is body weight, and zero is somewhere down here. Then the force stays zero until they land and resume contact with the force plate, at which point the force will spike and eventually reestablish itself at the body weight line. There are two key pieces of information that we can get from this graph of force as a function of time during the jump. One piece is the time of flight, the time that the person is in the air. And we'll talk about how to use that in a minute. The other piece of information that we can get from this graph is the impulse that's applied to the person. So the impulse is the area under the force-time curve. Remember that from physics, impulse of force with respect to time. And the impulse is equal to the change in momentum. So we can get both of those pieces of information from this. Impulse, we would use a trap z or cum trap z function in MATLAB if you wanted to numerically get all of these little bits of area. The time of flight, you can just find the points in time where this is zero. So these two different pieces of information lead to two different ways that we can think about estimating jump height. First one we're going to consider right now is the energy method. The energy method uses the idea of conservation of energy. Energy method, conservation of energy, and says, well, if energy is conserved, the initial energy total is equal to the final energy total. And assuming, so for energy to be conserved, the work done on the system has to be equal to zero. And work is defined as force applied over a distance. So anytime that we're in contact with the ground, there's work being done, so we can't do that. But while we're in the air, the time that we're in the air, work equals 0. So we could say, yes, energy is conserved there. So thinking about that, the mechanical energy, the total mechanical energy is kinetic initial plus potential initial, and that's equal to the kinetic final plus the potential final. And if we consider initial to be takeoff and final to be the maximum height where the velocity will be 0, we can make an assumption based on those and simplify the kinetic energy equation to be kinetic energy initial, potential energy final. We set H0 equal so that this is 0, and then the velocity is 0, so the kinetic energy final is 0. Based on this, we can come up for an expression for the maximum height in terms of the takeoff velocity. So the takeoff velocity squared divided by 2 times little g. And then we can combine that information with the area here, the integral of the force over time, to find the takeoff velocity. So you can do that in MATLAB. V takeoff comes from cum trap z in MATLAB, finding the integral, the numerical integral of force with respect to time. You can assume that your initial velocity before takeoff, or your initial velocity way back here, is 0. So then you can predict the velocity over time. Remember to look up help on cum trap z. And with that, you can get one estimate of the max height. The second method we're going to talk about is the time of flight method, where we measure how much time the person is off the ground. So the time of flight method, which falls back on kinematics, in particular this xf equals xi plus vit plus 1/2 at squared kinematics equation that you talked about in intro physics. So remembering that the definition of acceleration is the change in velocity with respect to time, and that while the person is in the air during this segment of the graph, acceleration is equal to little g downward. So then we can say that this is equal to vf minus v0 initial divided by tf minus t0, and that that's equal to little g. Again, assuming that t0 happens here and that at the top of the jump vf is 0 at the top, you can rearrange this into an expression for the initial velocity, or vi, equal to g times the time of flight divided by 2, since we're only halfway across. We can then take that definition, or that expression for velocity, and substitute it back into the kinematics equation and simplify, and we find that the height using the time of flight max method is equal to positive gt squared g t flight squared divided by 8. And this gives us a second way to compare the height. So you should be able to make a graph where you have the height with 3 different points. So the graph, you've got the graph here, and you've got your time of flight estimate. You have your energy method estimate, and you have your marker position, your actual estimate. So the marker, the time of flight estimate, and the energy estimate. So a graph with 3 different dots, each one with a different way to estimate how high the person jumped. And you're going to compare those graphically.